So in the past two lectures, we've discussed the basic study designs that are used in epidemiologic investigations. Regardless of which design is used, the ultimate objective is to determine whether there is an excess risk or perhaps even a reduced risk of a certain disease in association with a certain exposure or characteristic. So today we're going to be talking about different measures of association that we can use to explore these relationships between exposures and outcomes. The incidence of disease in a population is termed absolute risk. In an outbreak, incidence and attack rate are used interchangeably. Absolute risk can indicate the magnitude of the risk in a group of people with a certain exposure, but because it does not take into consideration the risk of disease in non-exposed individuals, it can't tell us whether the exposure is associated with an increased risk of the disease. Nevertheless, absolute risk may have important implications in clinical and public health policy. For example, a woman in a developing country who becomes infected with rubella during the first trimester of her pregnancy may ask her physician, what is the risk that my child will have a birth defect? And a certain number may be given as an answer. She's not explicitly given a comparative number, but she's making an implicit comparison. She's wondering not only what her risk is, but what would it have been had she not contracted rubella. So although absolute risk doesn't stipulate any explicit comparison, an implicit comparison is sometimes made when we look at the incidence of disease. However, if we want to address the question of association, we must use approaches that involve explicit comparisons. Although students often assume that these types of explicit comparisons are mathematically complex, it really comes down to subtraction and division to estimate probabilities. So let's consider the results of a hypothetical foodborne outbreak. What we would like to know is whether there is an excess risk of the disease in persons who have been exposed to a certain agent or food. So the suspect foods were identified, and for each food, the attack rate or incidence rate of the disease was calculated for those who ate the food, so they were exposed, and for those who did not eat the food, or the non-exposed. So how can we determine whether an excess risk is associated with each of the food items? One approach is to subtract the risk in those who did not eat the food from the risk in those who did eat the food. The difference then represents the excess risk in those who were exposed. An alternative approach is to calculate the ratio of the attack rates in those who ate each food to the attack rate of those who did not eat each food. So you can see in each of these two columns, I'm just subtracting and then I'm dividing. So the first column gives us a measure of absolute risk. The second column gives us a measure of relative risk. So as seen in the foodborne outbreak, to determine whether a certain exposure is associated with a certain disease, we must determine whether there is an excess risk of the disease in the exposed populations. We've just seen that an excess risk can be calculated in the following two ways: the ratio of risk, or of the incidence rates, and the difference in the risks. 2x2 tables are used in epidemiology to summarize the counts of those who have the disease and those who have the exposure. So this table sets up the numbers that we use to do our calculations of associations. Along one side of the table is always the exposure status. In this case, it's yes or no, but it could be more complex in terms of levels of association. And along the top of the table is the outcome status, yes or no. So in the previous table, or the table that you see in the bottom right-hand corner of the screen, cell A is the number who are exposed and have the outcome. Cell B is the number who are exposed and do not have the outcome. Cell C is the number who are not exposed but have the outcome. And D is the number who are not exposed and who do not have the outcome. We can also add the cells together. So if we add A and B together, that tells us the total number of people who are exposed. Similarly, C plus D is the total number who are not exposed, A plus C is the total number who have the outcome, and B plus D is the total who do not have the outcome. And lastly, if we sum all of the cells in the table, it gives us the total study population. So if we carry out a cohort study, we can ask the question, what is the ratio of the risk of disease in exposed individuals to the risk of disease in non-exposed individuals? This ratio is called a relative risk. And this measure indicates how much more or less likely one group is to develop the disease compared to another group. So cohort study is the only type of study where we can calculate a relative risk. So let's take a look at how we do that. To calculate relative risk, we need to determine the risk in the exposed and the risk in the unexposed. So we set up our 2x2 table. The risk in the exposed is the number of exposed who have the outcome. So it's cell A divided by the total number who are exposed, or A plus B. So that gives us the incidence of disease in the exposed group, or the risk in the exposed group. The risk in the unexposed group is the number of unexposed who have the outcome, which is cell C, divided by the total number who are unexposed, C plus D. So the relative risk calculation, we look at the total number of people who are in the exposed and unexposed group. So the relative risk is always the measure of association used in cohort studies because it was designed to compare the outcome among the exposure groups. So the relative risk in this case is A over A plus B divided by C over C plus D, or the risk in exposed divided by the risk in the unexposed. So here we see an example of a cohort study where we're looking at the exposure. This is data from the first 12 years of a cohort study of smoking status and the risk of heart disease. We have 3,000 smokers and 5,000 non-smokers that were followed over a period of time. Of the 3,000 smokers, 84 developed heart disease. The incidence of heart disease in the smokers is then 84 over 3,000, or the number with disease divided by the total number who are exposed. In the non-smoker group, we had 5,000 non-smokers, and 87 of the non-smokers developed heart disease. And so the incidence of disease in the non-smokers is 87 divided by 5,000. So if we divide the incidence in the smokers by the incidence in the non-smokers, we come up with a relative risk of 1.6. And a relative risk greater than 1 means there's a positive association between smokers and heart disease. We can say that smokers are 1.6 times as likely to develop heart disease as non-smokers. So now that we've calculated the relative risk, what do the numbers mean? If the measure of association equals 1, that means that there's no association between the exposure and disease. When the two groups were compared, they were the same. The measure of association is greater than 1, that means there's a positive association between the exposure and the disease. The group that has the exposure also has more disease. If the measure of association is less than 1, that means that there's a negative association between the exposure and the disease. The group that has the exposure has less disease. This is also known as a protective effect. Now let's talk about case control studies for a few minutes. The problem with the case control study is that we do not know the incidence in the exposed population or the incidence in the non-exposed population. That's because we're not starting at baseline and following people through time to see if they develop disease. In a case control study, we're looking retrospectively. So we don't have incidence. We can't calculate a relative risk. So what do? We calculate what we call odds or odds ratios. So if you think about betting, odds is often known as the ratio of money that may be won versus the amount of money that's bet. So in statistics, the odds of an event is the ratio of the probability that the event will occur to the probability that the event will not occur. So for example, in 100 births, the probability of delivery being a boy is 51% and the being a girl is 49%. So the odds of a delivery being a boy is 51 over 49, or 1.04. So in simpler terms, an odds of an event can be calculated as the number of events divided by the number of non-events. So let's borrow the concept of odds and apply it to disease and non-disease. The odds of having the disease is the ratio of the probability that the disease will occur to the probability that the disease will not occur. Or the odds of having the disease can be calculated as the number of people with the disease divided by the number of people without the disease. So if we look at a 2 by 2 table, the odds of having a disease in the exposed group is the same as the odds that an exposed person develops the disease. Let's look at our 2 by 2 table for a second and figure out how to calculate an odds ratio in a case control study. So we have exposure on the left-hand side, just like a cohort study. Yes, there's a history of exposure, and no history of exposure. And then the outcome, instead of having outcome as we would in a cohort study, we have case and control status. So the odds that a case was exposed is A divided by C, and the odds that a control was exposed is B over D. The odds ratio then is the ratio of the odds that the case was exposed to the odds that a control was exposed. So again, we're just using simple division here. A over C divided by B over D. So here's another example. This is a case control study that was conducted of children with and without autism to try to identify risk factors for the disease. So parents were asked about the medical history, and one of the questions that they asked was whether there was another sibling in the house and whether that sibling had autism spectrum disorder. So to calculate, so you can see the 2 by 2 table here. The outcome is a child with autism, yes or no, and the exposure is a sibling with autism in the house, yes or no. So to calculate the odds ratio, we multiply cell A by cell D, A times D, divided by B times D. We call this the cross product ratio. And essentially the way we get that is because if we go back to the cell, to the slide before, you can see that A over C divided by B over D mathematically is the same as A times D over B times C. We have to flip the fractions over if we want to solve this mathematical formula. Okay, so in this case we have 130 times 135 over 115 times 120. That gives us an odds ratio of 1.27. So from here we can conclude that the odds of having a sibling with autism are 1.3 times higher in someone who had autism than in someone who did not have autism. So we interpret an odds ratio very similarly to how we interpret a relative risk. If the odds ratio is 1, the exposure is not related to disease. If the odds ratio is greater than 1, the exposure is positively related to disease. All we can say is there's a positive association, but we can't say anything about the exposure causing disease. If the odds ratio is less than 1, the exposure is negatively related to the disease, and we can say that there's a protective association. So an odds ratio can be calculated in a cohort study and in a case control study. We typically don't use an odds ratio in a cohort study, but technically you can calculate it. A relative risk can only be calculated in a cohort study. And then the final step in testing a hypothesis in an analytic study is to conduct a test of significance. And so a test of significance is an indication of the reliability of the association that was observed. It answers the question, how likely is it that the observed association may be due to chance? We may think that we know the cause of a disease because the measure of association that we calculated was very large. Let's say we got a relative risk of 10. But what if that number is not reliable and we only saw that association because of chance? So we calculate this test of significance. There are two main tests of significance in biostatistics and epidemiology. One is a 95% confidence interval, and the other is a p-value. And if you've read anything in the medical literature, you always see these numbers following an odds ratio or relative risk. So the confidence interval is the range of values of the measure of association, the relative risk or the odds ratio, that has a 95% chance of containing the true relative risk or true odds ratio. So what we mean by the true relative risk or true odds ratio is the number that we would get if we had all possible data on every single person in the population and we didn't have a single error. But this never happens. So when we have a 95% confidence interval, we say that we are 95% confident that the true measure of association falls somewhere within this interval, right? So we may calculate our relative risk as 2.3, and then we have a confidence interval of 1.7 to 2.6. And so we can say, we think it's 2.3, but we're 95% sure that it's somewhere between 1.7 and 2.6. So here are some examples of 95% confidence intervals of a case control study of patients with and without fertility looking at their history of STDs. So a study of the association between infertility and gonorrhea resulted in an odds ratio of 2.4 with a confidence interval of 1.3 to 4.4. This is like saying that our best estimate of the odds ratio is 2.4, but we're 95% sure that it's somewhere between 1.3 and 4.4. And because that odds ratio is greater than 1, we can say that there's a positive relationship, that gonorrhea increases the odds of having infertility later in life. So there are a few other examples listed in the chart, and you can see that in every single case, the value of the odds ratio falls somewhere in the middle of the confidence interval. It always works that way. And so you also are looking to see whether the confidence interval includes, if the confidence interval includes 1, remember when on the interpretation slide that means that there's no association, so it's not statistically significant. So even though the odds ratio might be greater than 1, the confidence interval includes 1, that means that there's no statistically significant relationship between the exposure. Okay, so a confidence interval should not include 1. So if the confidence interval includes 1, there's no significant association between exposure and outcome. A confidence interval with both ends of the interval below 1 suggests less risk of the outcome in the exposed population. And a confidence interval with both ends of the interval above 1 suggests a higher risk of the outcome in the exposed population. So let's quickly talk about p-values. P-values are another test of statistical significance. The p-value is a measure of how likely the observed association would be to occur by chance alone, if there was not really a true association. So a very small p-value either means that you are very unlikely to observe the relative risk or odds ratio that you calculated if there was no true association. So we typically use a p-value of 0.05 as our cutoff point. And so p-value of 0.05 indicates that there is only a 5% chance that the relative risk or the odds ratio that you observed was due to chance alone. So let's go back to the case control study of STDs and infertility. And so here are the p-values that accompany the odds ratios and the confidence intervals. You can see that the p-value, the confidence interval, and the odds ratio are all in the same direction. For gonorrhea, we have an odds ratio above 1, meaning that there is a relationship between the exposure and the outcome. The confidence interval does not include 1, so we can say that this is statistically significant. And so the p-value is less than 0.05, meaning there is less than a 5% chance that the relationship is due to chance alone. So you can see that the relationship between herpes and infertility does contain 1. The confidence interval does contain 1. And in that case, the p-value is also greater than 0.05, which makes sense. So if the confidence interval is not statistically significant, the p-value should be greater than 0.05 and also not statistically significant. So just to sum up on the p-value, the p-value indicates the probability that the findings observed could have occurred by chance alone. However, a non-significant difference is not necessarily attributable to chance alone. So if we have a very small sample size, sometimes we can see a non-significant p-value. And that doesn't mean that it's not a real effect. It just means that we don't have enough power, we don't have a big enough sample size to see a difference if it truly did exist. So, just to sum up everything we've talked about in this lecture, selecting the appropriate measure of association depends on the study design. For a cohort study or clinical trial, we use a relative risk. For a case control study, we use an odds ratio. All measures of association should be accompanied by a 95% confidence interval and p-value to help interpret that measure of association and determine whether it's statistically significant.